Even though the equation has a degree 5, it's easily split into the equation of degree 2. First, we just observe that we have a trivial root, x equals 0, which is totally irrelevant for our consideration because this number we're looking, this number is a non-zero number. The remaining part is the quadratic. Essentially, this is a quadratic equation which we can solve via the quadratic formula. Here I apply the formula. I hope you know that formula. We come up with two numbers, and then the place we stopped, we were in the process of deciding which number out of these two will correspond to my sine pi and 5. My suggestion was to make this observation. We have another angle which basically suits the same line of argument because it's another angle between 0 and 90 degrees. This one is 36 degrees, this one is 72 degrees, if you care about the degrees. So this angle will fit the same line of argument. The left-hand side here will be 0, so it will also be, if you take the x equals sine 2 pi on 5, it will also be the solution to this equation, and that's so it will be also among these two numbers. And then we can choose easily because the sine of this angle is larger than the sine of this angle because sine is an increasing function. So the one with plus will be the sine of 72 degrees, whereas the one with minus, under the square root, of course, will be the sine of 36 degrees. So if I choose the one with the minus, here's my expression for sine of pi and 5. I just apply the square root because here we have x squared. I apply the square root. And that's the expression we have for the sine pi on 5. Just by itself, it's a very interesting result. I mean, beside those standard angles, pi on 6, pi on 4, pi on 3, I don't think you know any other angles for which you know value of sine and cosine exactly. Not like I think 1 point something or 0 point something 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 from your calculator, but the exact sharp value. You have only 3 values within the first quadrant. Pi on 6, pi on 4, pi on 3. Here's another one, which we discovered via this lengthy process. It's another value for which we now know the sharp value. It's just by itself, it's quite an achievement, I'm telling you. But this value has a connection with the perfect pentagon. I already just outlined this connection last week. Let me just zoom out a little bit. The connection goes like this. Well, perfect pentagon, if you inscribe this perfect pentagon in a circle of radius 1, the side of this perfect pentagon will be exactly double of this sine. You derive this from this triangle. So double of this sine, it's the side of my perfect pentagon. So if you just remove this 1/2 from here, that will be the side, this expression. This is the expression for the sine of the perfect pentagon. Now I'm going to alter this expression a little bit. I'm going to just make it a little bit larger. You may not like it, but you will see the reason for that in a second. Look what I'm going to do. I will make this observation, that the same sign, well, I'll keep the 1/2 in front, nothing wrong with that. But under the square root, the expression, I will alter as follows. Look at this. Like this. If you ask me why did I do that, you will see the reason, very clear reason in a second. But if you just check the arithmetic, it's a true modification. It's a correct modification. If you expand this bracket via binomial formula again, square of this plus square of this plus this 1 will just return exactly 5 on 2. And the double product within this bracket, if you do the binomial expansion, will be this term. So it's a proper replacement. Even though you may not see the reason for that yet, but it's a proper replacement. Now, the reason for this replacement is this. Let's just try to picture this number here now. Look at this. Well, remember, this perfect pentagon, it is inscribed into unital circle, right? The radius here is 1. Now, if you take this another radius, perpendicular radius to your vertical one, here you have, let me just make it a little bit thicker, if I can find that. Just make it a little bit thicker. Yeah. So here's the one radius, 1. Here's another radius. This is the middle point of that radius. Now, it's a triangle with a 90-degree angle. One side is 1/2, the other side is 1. What's the hypotenuse of that triangle? Root 5, isn't it? Root 5 on 2, in fact. the hypotenuse of that triangle. What's happening? I'm sorry. The hypotenuse of that triangle is this. Right? 1 plus 1/4. 1 square plus 1/2 square, here's 1/2, plus 1/2 square, which is 1/4. 1/4 plus 1/4 plus 1, it's 5 on 4. Under the square root, it will be root 5 on 2. Isn't it? Now, imagine imagine I have a compass, this device which allows you to draw a perfect circles on a piece of paper. Relatively easy. Imagine I have a compass and I put one leg of the compass in this point, and I open the other leg all the way up to this point, and I just drag it down and I make a mark here. You see this dashed arc? That's the trace of my imaginary compass action. Then this piece of the diameter from the center up to this point will be this length. Take away the half of the radius, which is 1/2. So this will be this value, the value in this bracket. Now, if you now look at this triangle with this red hypotenuse, and if you apply the Pythagoras theorem again, the side of this red hypotenuse will be this value under the square root, isn't it? Because it's a Pythagoras square of 1, here it is, and square of this side, here it is. Meaning that the whole square root, this square root, remember 1/2, we don't need the 1/2 because the side of my pentagon is double of this side. So the sine of the pentagon, this root. And so the sine of the pentagon is this hypotenuse. So if you take compass again, put your leg of the compass in here, take the radius up to this point, which now you know the position of, and you drag it across here, you can make a mark on a unit of circle, and you can mark the side of the perfect pentagon.